Hi, this is Zach Langley, a PhD student at Rutgers University, and today I'm going to be telling you about some joint work with Aaron Bernstein and Aditi Dudeja titled A Framework for Dynamic Matching in Weighted Graphs. Let me start with some basic definitions. A matching is a set of vertex disjoint edges, as depicted here in blue. A maximum cardinality matching is, as the name suggests, a matching of maximum size. In this graph, the maximum cardinality matching is the one depicted, which has size 3. I'll use the notation MCM of G to denote the size of the maximum cardinality matching of G. In an edge-weighted graph, the weight of a matching is the sum of the weights of the edges in the matching. For example, the matching depicted here in blue has weight 6 and is the unique maximum matching in this graph. I'll use the notation MWM of G, when G is weighted, to refer to the weight of the maximum weight matching of G. Now let me define the dynamic graph setting. In the dynamic matching problem, the input graph undergoes updates over time, and the algorithm must maintain a matching over these updates. Depicted on the right is a graph G and a matching M in blue. The algorithm script A processes updates to G to maintain the matching M. For example, perhaps when this green edge is inserted into G, the algorithm chooses to include this edge in its matching. Of course, the algorithm may make many changes in response to a single insertion or deletion, not just one. The goal is to process each update quickly while maintaining a large matching at all times. The two main criteria on which a dynamic matching algorithm is judged are its approximation factor, or approximation ratio, a lower bound on the ratio between the size of the matching maintained and the size of the largest matching in the graph, and the update time, the time it takes to process an update, which can be worst case or amortized. Okay, our first result is a black box reduction in the dynamic graph setting from weighted bipartite matchings to unweighted bipartite matchings. Namely, we show that any algorithm for the unweighted problem gives an algorithm for the weighted problem with nearly the same approximation ratio and update time. Let me highlight a few consequences of this result. In the unweighted world, there are many different trade-offs between approximation ratio and update time. For example, there's an algorithm that obtains a nearly 1/2 approximation in polylog and update time, and there's an algorithm that obtains a 2/3 approximation but takes m to the 1/4 update time. The third algorithm listed here shows that you can have an algorithm that takes arbitrarily a small polynomial update time and still beat a 1/2 approximation. All of these unweighted algorithms, through a general reduction of Stubbs and Williams, give rise to weighted algorithms that have essentially the same update time but lose a 1/2 factor in the approximation ratio. Our result shows that for bipartite graphs, all of these unweighted algorithms actually give weighted algorithms with the same approximation guarantees. For non-bipartite graphs, we actually also improve the approximation ratio. So rather than losing the 1/2 factor, we have a black box reduction that loses a 2/3 factor. So for general graphs, the unweighted algorithms on the left give weighted algorithms with the properties here on the right. However, for non-bipartite graphs, we can actually further improve these top two results, though not in a black box fashion. By proving properties about the structures maintained by these algorithms, we can show that even in the general non-bipartite case, we can match the approximation ratios of these two unweighted algorithms. Okay, so now let me explain our bipartite framework. In this talk, I'm going to assume that all edge weights are integers between 1 and w. You can think of w as a very large constant for constant epsilon. It's exponential in 1 over epsilon. This assumption is based on a bucketing scheme by Gupta and Peng that reduces from the arbitrary weight case. And if you're curious about the details, you can see their paper or see our Appendix C. Next, we'll need a dynamic weighted matching algorithm for bounded degree graphs. In our paper, we describe a simple algorithm that maintains a 1 minus epsilon approximate maximum weight matching in update time delta times w squared over epsilon squared, where delta is the maximum degree of the graph. If you're familiar with the dynamic unweighted matching algorithm by Gupta and Peng, this is basically a weighted analog. The algorithm works by lazily recomputing an approximate maximum weight matching from scratch using an efficient static algorithm. The final ingredients we'll need are graph unfolding and refolding. Let me start with unfolding. Given a weighted graph G, we form the unfolded graph, denoted phi of G, as follows. First, we make W copies of every vertex. We also make copies of every edge in G, where the number of copies in phi of G is given by the weight of that edge. For example, the edge UV on top has weight 2, and therefore has 2 copies in phi of G. The copies are connected so that the sum of the copy IDs are equal to the edge weight plus 1. You can read the formal statement at the bottom. The following theorem says that for bipartite graphs, the size of the maximum matchings in the original and unfolded graphs are the same. One direction is clear, since every matching in G corresponds to a matching in phi of G with the same size. Just take all the copies of each edge in the matching of G. The other direction is less clear, since matchings in phi of G might not use all the copies of each edge. Nevertheless, for bipartite graphs, the theorem says that you can never increase the size of the matching by unfolding the graph. When we have a subgraph H of an unfolded graph, it'll be useful to talk about the subgraph of G that gave rise to those edges in H. We call such a subgraph a refolded graph and use the notation script R of H to denote it. In precise terms, an edge is in R of H if and only if at least one of its copies was in H. Note that if H is a matching, then R of H has a maximum degree W. We'll use this fact later. An easy corollary of the unfolding theorem from a few slides ago is that in bipartite graphs, refolding can only help in terms of the matching size. Using the example from the previous slide, the subgraph H of the unfolded graph has a maximum matching of size 3. After refolding H, we obtain a subgraph of G with a maximum matching of size 4. The proof is a one-liner. First, observe that unfolding R of H gives a supergraph of H. Indeed, phi of R of H will just have every copy of every edge represented in H. Thus, the maximum cardinality matching only increases under this process of refolding and then unfolding. Okay, but then by the unfolding theorem, the maximum cardinality matching of phi of R of H is equal to the maximum weight matching of R of H. Okay, I'm now ready to describe our bipartite reduction. In the top left, we have our graph G, and suppose that we were also given an unweighted matching algorithm A of U. We're going to use AU to maintain a matching over the unfolded graph phi G. To implement this, we simply forward the W updates in phi of G to AU that correspond to the update made to G. For example, suppose we insert an edge here of weight 3. This edge corresponds to 3 edges in the unfolded graph, so we feed these 3 edges as insertions into phi of G. These updates can trigger both insertions and deletions in M sub phi, the matching maintained by AU. Here I'm depicting insertions in green and deletions in red. Note that if we wanted to merely maintain the size of the maximum matching, we'd be done here because phi of G and G have the same size maximum matching. However, since we want to actually maintain an explicit matching, we need to do a little bit more work. Tracking updates to M sub phi, we can deduce updates to the refolded graph R of M sub phi. For example, the updates made here correspond to a deletion and an insertion in R of M sub phi. By the refolding corollary, R of M sub phi contains as good a matching as M sub phi itself, and thus if we simply use the 1 minus epsilon approximate matching algorithm AB mentioned earlier, we'll maintain a good matching of G. The update time has 2 components, the time taken by AU and the time taken by AB. Using the fact that R of M sub phi has maximum degree W, we obtain the bound given here. As an aside, note that this framework is quite general and can be applied in other settings besides the dynamic one. Indeed, we show that our framework can be used to obtain weighted analogs of unweighted results in both the streaming setting and one-way communication complexity settings. Okay, in the last section of this talk, I'll show you how we can apply our framework in the general non-bipartite case. Let me start by demonstrating what goes wrong with unfolding non-bipartite graphs. Consider the simplest non-bipartite graph, a triangle. If we give every edge of the triangle weight 2 and unfold this graph, we obtain the graph C6, a cycle on 6 vertices. Hence, the unfolded graph has a matching of size 3, whereas the maximum weight matching in the original graph had weight 2. So the unfolding theorem that matching size is preserved does not hold in non-bipartite graphs. Additionally, the refolding corollary doesn't apply. Suppose G was a triangle with 3 spokes on the left, and all edges had weight 2. This graph clearly has a matching of size 6 given by the spokes. Now suppose we maintained a maximal matching, a 1/2 approximation, in the unfolded graph, as shown here. When this maximal matching gets refolded, we obtain the blue triangle on the right. Note that this triangle has a maximum matching of size 2. Thus, the approximation ratio of the maximal matching has been compounded with an additional 2/3 factor loss from refolding. Fortunately, dynamic graph algorithms don't typically maintain just matchings. They maintain more complicated structures that, as we will show, are resilient to this refolding loss. For example, the 1/2 approximate polylog n update time algorithm maintains a subgraph called a kernel, which I'll now define. A kernel is a subgraph with 2 parameters, d and epsilon. D epsilon kernels satisfy the following 2 properties. First, the kernel has maximum degree d. Second, if some edge is missing from the kernel, that is, it's present in G but not in the kernel, then one of its endpoints must have degree nearly d. To gain some intuition for this definition, note that a D0 kernel is just a maximal D matching. Using non-zero values for epsilon gives some slack in this maximality constraint and thus makes the subgraph easier to maintain. Here are 2 known and useful properties of kernels. First, they contain approximate maximum matchings. This complicated looking factor here should basically be read as nearly 1/2. Second, kernels can be maintained in polylog n update time. We prove an additional fact about kernels with respect to refolding. Essentially, we show that kernels do not lose that 2/3 factor from refolding that, say, maximal matchings do. Provided that D is taken to be sufficiently large, refolding a kernel only loses a 1 - epsilon factor in its maximum matching. The proof of this theorem uses the probabilistic method. Okay, so with that theorem in hand, we get a very similar framework to the bipartite framework from the last section. Using a dynamic algorithm BU to maintain a kernel, we have the following illustration of our 1/2 approximate polylog n update time algorithm for general graphs. This picture is almost identical to the bipartite framework, the only difference being the black box now maintains a kernel instead of a matching. It's easy to see that any subgraph that does not suffer from refolding can be used in this framework. Okay, this motivates the following definition. If a subgraph loses a factor alpha when refolding, we say that it's alpha refolding approximate. We've already claimed that kernels are 1 - epsilon refolding approximate. Matchings can be shown to be 2/3 refolding approximate in non-bipartite graphs, which gives the black box reduction that loses the 2/3 factor. Finally, in our paper we prove another structure, the EDCS, is 1 - epsilon refolding approximate. This is the subgraph used by the 2/3 approximate m⁴ update time algorithm, and proving the EDCS is 1 - epsilon refolding approximate is how we match the bounds of that algorithm. Okay, so that's all I wanted to say in this talk. Let me just conclude with some open problems. First, it would be great to reduce the dependence on epsilon. Currently, by using Gupt and Peng's bucketing scheme, we suffer exponentially in 1 over epsilon in the update time. I also mentioned that this framework applies beyond dynamic graphs, and we've obtained interesting results, for example, in the streaming setting. Are there other settings in which it applies? And lastly, a more general question in this space is, are there efficient dynamic algorithms to maintain kernels deterministically? All kernel algorithms we know are randomized. Thank you.